Hello, Chad.
Yes, Professor.
How did it go with you?
Good.
Okay.
Yeah. It's
You are done with all assignments?
I haven't turned in.
What is missing?
Just the last homework 4. I'm still working on it.
Okay. I believe we spoke earlier about generic. Have you all looked at this program? Vitaly,
Yes.
have you looked at this one?
I remember looking at it in our last lecture, yes.
Okay. So you know what is meant by generic, this statement, where I can specify these bits, I specified as integer of 8, and then if I want to make this program, which is a counter, 16-bit, 32 bits, I just change it from this point.
Right. Isn't it a more efficient way of controlling how many
Yep.
signal paths you have?
Yep.
Perfect.
And then we spoke about having multiple generic. This is the terminal count. 255, 0 to 255, and I am using it here with this command in here. This command, what it does, it is converting the standard logic. This is the terminal count I have, 255. I'm converting it as a 7-bit, 8-bit, because I have terminal count, the bits is 8. So I'm using the terminal count 255 as an 8-bit. I'm converting it to a binary number. This is the binary. So this command converts standard logic vector. It converts this decimal number 255 as 8 bits. Since it is 255 and 8 bits, all bits will be 1. so I can use it in the comparison. Comparing the counter and this counter I am comparing, it is comparing it with 8-bit binary number.
Professor, I noticed that you don't specify for all the bits and the counter and the converted standard logic to be 1. So does it convert them to 1 by default, and you have to specify otherwise?
Here, I wanna see if I have reached the terminal count. Counter is incrementing up, 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 up. When it reaches 1, 1, 1, 1, I want it to reset to 0. This is the second one. So I am comparing the value of counter, which I specified as 8-bit standard logic vector, 8-bit standard logic vector. So I have to have 8-bit.
I think I just answered my question.
I cannot compare it. I cannot compare it. This is standard logic, that is 8-bit. I cannot compare it with 255. 255 is decimal, not binary. So I need to convert it to binary. How many bits in binary? 16-bit, 25-bit. So I am saying here, convert TC, which is the terminal count, that's 255. And the span of it will be 8 bits.
That was perfect. I just totally forgot that TC was included in that command. Perfect.
Yep. Okay. And this is where we stopped last time about the generate statement. This generate statement, I showed you in our last lecture how I can have a component that is a little program that I can call and use. We saw it in a full adder. Here we are going to use the same component, a different component that is for shift register. So this is my main program right in here. And this main program, it is using generic bits, that's 8 bits. And those are my IOs of this program, shift register. All are in here. Okay. This shift register, it is using D flip-flop. As we saw last time, I have 8 diff flip-flops. And since this is serial in, serial out, the first flip-flop will get the D in. And this D in will come here and go to the next one. Go to the next one. Go to the next one. Finally, I will have this, my output. So I have D in and I have output. And all of those are controlled by a clock. Going back in here.
May I ask a quick question?
Yes.
On that past slide, it went in from the left and went out to the right. Is the left the least significant digit?
Yes, least significant digit. Yes,
Thank you.
thank you. So I have D in and D out. And of course, I have a clock. What else do we have? I have reset or shift and shift. Reset is to reset everything to 0. Shift, when high, D in 0 will go to D in 1, and so on. It will propagate. And please note this red line means signal, internal signal. Now, what do we have? This is the architecture. This is the signal I have. Jose?
Yes, Professor.
How many red lines do we have?
Oh, 3.
This is 8-bit.
3.
No. Here it is dotted, means there are more, but I didn't put the 8 of them.
Got it. So then
We have 8 boxes.
if there's 8 boxes, then there should be 7.
Excellent. That is why my signal, it is bits minus 1. Bits is 8. So 7 down to 0. Now I have a D flip-flop. This port component, D flip-flop, this is a different program that I'm gonna write, and I'm gonna follow the same steps we specified in writing last time. Where do I have it? Here we are. Create folder, but this was for the full adder, adder 8, new project, adder 8, new VHDL full adder. This is our small program. This will be my D flip-flop. Compile, add to the project. Now, new VHDL adder 8, compile, and use wave4 to see the output. We're gonna do the same thing, but with this program. So I made this component, and those are the ports. I copied those as is from the entity of my D flip-flop. D flip-flop, it is very simple. The output will be the input. This is the D flip-flop. Of course, we are governed by a clock, we are governed by reset, we are governed by a shift, if there is a shift. Now, I have my first block. This is D flip-flop 0. D, F, F, 0. This is the first one. it has DN, it has clock, it has reset, and shift. And it has also out. For this one, as you can see here, first D flip-flop. D, it will be the D in. D in, this is my main program coming from outside. And its clock will take the clock from outside. Shift, I called it in my D flip-flop small program enable, so shift will be enabled. Please note here Q, it is connect 0, connect 0.
Professor,
Yes, sir.
please, can you tell us again the function of the shift again?
Shift, you are inputting here D in. When there is a clock and the shift is high, it will propagate and it will be the output here. And if I have another clock, it will move from here to the next one, to the next one. After 8 clocks, it will reach the output. So the stream coming from D in, it is propagating until it reaches the output. Clear?
Is it acting like a delay of the output?
In a sense, yes.
Okay, thank you.
So this is the first one. The first one was very special because it is taking D from the input. D is coming from outside. But now we go to the next one. The next one, I can repeat the same thing as I put in here. I can repeat it 7 more times. 7 more times. And I'll make sure that in this case, D not will be D in, it will be D in of the previous stage. That's connect n-1. And the Q will be connect 1. What about the next one? The next one, D will be connect n-2. Here, this line is my first connect. And this is my second connect. So the output of the first one will be the input for the second one. Output of the second will be the input of the third. And this is expressed in here. D will be connect n-1. And Q connect n. This is repeated for n1 up to 7 bits. 8 minus 1, that's 7. N generate. I am repeating this 7 times plus the first starting one. That makes it 8 D flip-flops. When I end with those, I am ready to go to D out. D out, what will be D out? This one. This one, if this is DF0, this is DF7. My output will be DF7. DF7 here, connect 8 minus 1, that is 7. So I am output this to the out. Any more explanation? Hello, hello. Clear?
Professor, really quick.
Yes.
Right after you call the first D flip-flop and you call the next one G1, could you name that anything?
G1 is repeated 7 times.
Okay, so I'm assuming it comes from generate.
Yeah.
Okay.
Generate here. It is a statement that can repeat the generation of the same D flip-flop.
No, yeah, that part makes sense. It's pretty efficient. I like that you can instantiate the n number of flip-flops, but could you
Yes.
can you name G1 anything? Did you just name that arbitrarily?
No, just name it Vitali. No problem.
Okay. Okay, so that doesn't matter. Okay, perfect. Thank you.
Okay. But here you have to end the same name. End generate.
Perfect.
Clear, Vitali?
Clear, Professor. Thank you.
Samuel? Samuel? Hello, Samuel? Hello, Paige?
Yep, it's all making sense.
Okay. I'll give you 20 minutes to do this program. And please let me know when you are done. If someone finished before 20 minutes, please let me know.
So wait,
Not more. I need this program.
Professor, so on last Friday, you had us doing the adder 8. You don't want us doing that one? You want us doing this one?
This one, have you done it?
The adder 8 part, right? Or the one that you showed us last Friday that we were doing?
No, the adder 8 that was on the first lecture.
Okay, so, yes, but you said you wanted
it
us
was
to
a
do-
training for this one.
Okay, okay. So you don't want us to. Okay, we don't. I thought
Do you have the adder 8 ready?
Yes.
Would you please show it to us?
Sure, I can do that.
No, I need explanation of whatever you have, starting from line 0.
Oh, sorry. I thought I was unmuted there. I was talking there. I apologize.
No.
Okay. So first I declare the entity that this is going to be, and this was from this first lecture, right? Because this was the thing we made, right? That was supposed to be the full adder.
This is our full adder, and this is the small component that will be calling.
Right,
Okay.
right.
Yes.
And then so I add that in the entity here and make a separate thing that's going to be the 8-bit full adder that has 8 bits for each X in, Y in, and the sum.
Yes.
And then I have the signals here that are going to be connected to the actual component of the adder. And then I have I declare the component full adder, which is the same thing as this part over here.
Yeah,
And then I have to declare the first component to be a separate thing because CN has to be equal to the first CN, which is from the input of the entity, right?
excellent, excellent.
And then you generate it with the 8 bits, and then I have it, so I can go over here. I think I can see it was working earlier. And I'll just have it count up by 1. Do it like this. And then this one can count every 1. Then I will make a carry in over here. Okay, and give it a sec. And there you go. You see it counts up to the 8 bits here, and then it has a carry out when we get to past 1111, and then it loops back around. And then of course when the carry in starts again, it adds it together. And I think I checked it already, so it should be okay. So that is what I have.
Excellent. Thank you. So any one of you have the option to use the generated statement with the shift register or the full adder, whatever you like.
Professor, I have a question.
Yes, sir.
Can you please pull up the slides really quick where you have the generate script?
Okay, just a moment.
No worries.
Yes,
Okay, so you see how in your component declaration, it says component is DFF, D flip-flop.
yeah,
So if I was to use one of the files that I created for a shift register, would I type the name of that entity there?
it must be called DFF.
Oh, so component must be DFF regardless.
Yes.
So where would I modify the name of my smaller program that I'm inputting into this?
If you change it in the small program, you have to change it here.
I see. So are you saying that I need to change my small program name to DFF?
Yes.
Okay. Is that going to mess up how it's stored?
No.
Or it
No.
should not?
No,
Okay,
no.
perfect. Awesome. Thank you.
Vitaly,
Yes, Professor.
share the screen with your DFF.
Okay, 1 second. Okay, so this is my original DFF. It was the load shift register 16-bit. So you're saying that I can rename this to DFF?
No, this is a shift register.
Right. So this is a actual shift register program where you have the component DFF.
Where is the file that's called DFF?
I'm not sure if we ever have had an exact DFF file. It was just within the shift register homework.
Just a moment. This is your new one. I'm asking about the DFF. Where is it? The small program that is called DFF.
That's my question. I'm not sure if we ever made an individual small program called DFF, or was I supposed
You
to make
make
one for
one.
this?
You make one. Make one.
Ah, for this make one. Okay, perfect.
Yes.
That makes more sense. Thank
Okay.
you.
Hello, Benar? Benar?
Hi, Professor.
How is it going?
It's coming along fine.
Okay.
I did the initial one you asked her to do on Friday, but I'm working on this one.
Oh, you have the one on Friday and it's working?
Yes, I emailed it to you over the weekend.
Could I see it now? Share the screen and so
Yes.
we can all discuss it.
All right, just a minute.
Could I see the full adder one? Yep. Can you all see? This is the small program, the component, and as you can see here, the entity. It is, the port is copied as is when we go to the component. Okay, now we go to our main program again. Would you please explain what do we have? We are not hearing you. We cannot hear you.
All right.
Okay.
Yeah, here we have the entity, the other 8 as our entity. Here are the ports. We have A, which is declared in standard logics, 7 down to 0, and B, the same thing, and the same.
Yes.
And we have, essentially, we have 3 input and 2 output here.
Excellent.
And other in the architecture, the component declaration component is the forward. I call it forward one because I tried it a few times, didn't work. But
Bernard, I have some advice.
yes.
I believe that your example program, the small one, full adder 1, has a capital F, and your component is lowercase f.
Okay.
I'm not sure, but I believe they have to be case sensitive.
Yes, as long as there's consistency, it would recognize it. So, but I appreciate that. Yes. In the port, we have X, Y, and C as input, and the sum and the C out as our output.
As you can see here, the port, the entity adder 8A, this is A, B, C in, S, C out. And as you can see here, we have standard logic 8 bits, but the full adder 1, it is just 1 bit. It is making 1 block only. Yes, continue, please.
Yes, and for the wave, let me
Would you go down?
Yes.
Go down? Yes.
So we add components, and in the internal carrier A bits, we have the signal with the class signal still as a signal
Yes.
7
Yes.
down to 1, and that's 8 bits, and begin the full adder. So it goes through the process, the full adder 1. It goes through this and up to seven. So it goes,
Excellent. Excellent. Cameron Castello,
Yes, Professor.
would you please show us your program? I
The
want
adder
you
8.
to see the difference between Bernard and Cameron. Cameron, yes. Can you see here the generate statement? The generate statement. He used one generate statement to generate bits 1 to 7. The program that Bernard showed, he repeated that several times, 7 times. But here, this is the power of the generate statement. This is the power of the generate statement. Both of them will give you the right answer. But suppose that I am making 32-bit adder. I will repeat it 32 times, 31 times. That's too much. That's why this generate statement will be very, very powerful. Would you stop sharing the screen? Please try to finish this program or the full adder, either one of them, with a generate statement. I want to see just the generate statement. And of course, if you have any late assignments, please try to complete those. Okay? And next week, on Wednesday, we are going to be speaking about switch bouncing. Okay? Thank you all so much. If you have any question, you have my cell phone number. Don't hesitate to call me.
thank you, Professor. Professor, please, I sent you an email about lab
About?
2 and homework 4.
What about it?
If we can get extension to turn it in tomorrow,
When is it due?
Sunday.
The coming Sunday?
No, yesterday.
Yesterday.
I
Okay.
sent an email to you yesterday.
This is the vending machine.
Yes.
Okay, I'll extend it for you. Thank you.
Thank you.
Professor,
Yes.
same with me, for yesterday's homework.
What homework? Homework 4 that was due Sunday. Yes. I'm going to extend it.
Oh, okay. Thank you.
Thank you.
We'll see you tomorrow.